So please.
So hi everyone, again, I'm Rona. I organize Women Who Go Berlin. I'm active in the Go community. I'm a Google developer expert for Go. And what else am I doing? I organize the diversity scholarships for Go Bridge. Unfortunately, those scholarships are currently on hold because well, nobody's traveling. So it's kind of sad, but it is what it is. You should minimize this if you don't see yourself. Sorry. So a few months ago, I went down this very strange rabbit hole about semaphores. Somebody, I think it started with somebody asking at a Go course that I gave. Somebody asked if the sync package had semaphores, and I said no, but I actually had no idea why. So I decided to go ahead and look. And I found multiple things, and I want to share sort of my journey with you, and I want to share, well, I call this talk Semaphores Correctly. Seriously, how? Because it's very, very hard to figure this out. It's not easy figuring out how to do them properly. And I'm still not sure, by the way, that I have the entire picture, but at least you will see what I see at the end of this. Oh, sorry. So what are semaphores? So if you're not familiar, imagine Monday morning at the office. I know it's a bit of a dream right now. There's 3 coffee machines. So this little square here is the what one might consider the universal icon for coffee machines. And obviously 3 coffee machines can serve 3 people. And then we have a bunch of other people who are waiting in line, probably not very happy. And at some point you might give up. If you're me, I usually just go back to my chair and try again later. But what if you could be notified when a coffee machine becomes available? And this is actually how it works on a technical level with the signaling process. So we have finite resources of something that need to be shared across a number of, let's say, Go routines or threads, or Go routines are lightweight threads, but anything that is that can run concurrently. So in computer science, we refer to this as a thread. And so we have a finite resource or finite resource. Figure out how to pronounce that word and let me know later. And when when a resource becomes available, somebody from the queue or from the pool who's waiting can take it and then release it, etc., etc. So it's a way to limit concurrent access to a resource or a group of resources. And in code, you cannot, like for instance, you cannot support more than 1,000 requests concurrently. So then you might want to just limit the number of connections that you accept into your server to 1,000. That's one example. You can't open multiple files, so you might want to change that. And then we have Semaphores and Go. So Go has Go routines, which is a lightweight thread, as I said, for running things concurrently. And Go also offers channels, which is essentially a queue. And it's a way to communicate safely between Go routines. And channels have capacity, and this is very important. So you have a buffer. If the buffer is empty and a Go routine is trying to read from the channel, it will block until there's a new item in the channel. And if the buffer is full, it's the same thing. If somebody is trying to write to the channel while the buffer is full, it will block until another reads from it. So there's signaling involved. You can already guess. So a common technique to have semaphores in Go, and this is from Effective Go. And if you're not familiar with this blog post, you should be. And so they create a semaphore that is essentially a channel of integers of the size of max outstanding, which is some constant, maybe 10, maybe a million. And then the function handle that should be, we assume, should be run concurrently for multiple Go routines will obtain a semaphore, or will acquire a semaphore by writing to it. So if we're the first ones, and let's say that the buffer is 1, max outstanding here, the capacity is 1. So we have 1 space for 1 item. Then we know that we can write to it because we're the first. So we're writing 1 into the buffer or into the channel. And then we process the request. Now let's say that we're still here. Another Go routine comes in and they want, or she, or it, or if, or he, wants to acquire the semaphore. So they're stuck here because we know that the channel is at capacity. We only had 1 room for 1 message or 1 item, and we already wrote to it. So it will block and it will wait, and it will wait here. We'll be stuck here. Now our first Go routine proceeds as usual. Process R reads from the channel, and now the semaphore is released, and therefore our second Go routine can come in and acquire, and so on and so forth. And this works to any number of n, to any n max outstanding, basically, as long as you don't reach the number, you don't exceed the number of Go routines that you can run on your machine. So now we have a problem with this. So the Go routine to execute handle is clearly created outside of handle because we're not looking at it, right? We're not seeing it here. So if process takes, if a process like this function here, the process request, takes a long time, we can run out of Go routines because we could be creating multiple Go routines, calling handle, handle, handle. Like we have a lot of requests to handle. And process is taking a long time. We don't have enough, max outstanding is low or is too low. And we could be running out of Go routines and crash. And we actually don't have, it's also maybe an issue. We have no control of how many Go routines we're running on the machine. So, so which is faster also? To spawn first the Go routine and then lock, which is what essentially happens here. Or maybe lock first and then spawn a Go routine. So maybe we should be creating the Go routine inside the sema, inside the semaphore code inside here. So the code that we want to do like a critical section for. So we have, let's consider 2 approaches. One is that we make the semaphore, like in both versions, we're going to make the semaphores. The semaphore in one, we're going to spawn the Go routine first. This is what we were seeing already. Like this basically assumed the same thing that we just saw. And in the other approach, we are going to, we're going to first acquire the semaphore by writing to the channel and then start a new Go routine. So in the first one, we have no control over the number of Go routines. Sorry, you probably can't see this. Maybe I can move this here. Every time I use this thing, just, that's unfortunate. 1 sec. I have nothing, I have no way of controlling this thing. So I'm just going to stop moving. Maybe this, better. Professional help, anyone?
Sorry, I'm not a Mac user.
I can't get rid of the thing at the bottom. Anyway, so let's hope that right now it's not covering anything. So let's hope it doesn't cover anything later. So in the first approach, we don't actually have control over the number of waiting Go routines, because there could be a bunch of Go routines that are just waiting to execute and they're accumulating. And in the other approach, we have control over the total number of Go routines. We actually know that we're not going to be creating. So in this incident, we used 10. So we know that we're not going to spawn more than 10 Go routines, but maybe this is actually slower. So let's find out. So I wrote some code, and I can actually help you. Sorry, I can actually show it to you. You can actually follow it yourselves here. Not here. At GitHub, I don't know if you can see this, github.com, Rona S. I will write it in the chat real quick. And then we can do this. I can't find the chat. Oh, this is funny. Oh, there it is. What do I click on? Chats here somewhere? It was here. Not
What do you want to show now?
This is not relevant. Wait 1 sec. Sorry. I am looking for the chat. And there it is. It's on the right hand side. Okay. So this is the link. Thank you. So this is the link to the repo. So I'm basically going to start comparing approaches to this problem, and then we're going to benchmark all of them and figure out which is correct. So I'm hoping that you can see this well. I created this function process that takes the max handler, or the weight of the semaphore, whatever you want to call it, and a slice of requests. Now we have some wait group here and some mechanism here to have some idea of when we finished. This will usually also exist in any kind of application that handles requests. Like, we would want to know when we're done, or we would not want to know when we can terminate it anyway. So I took the liberty to keep this, or to use this to my benefit for benchmarking. So we're taking a slice, we're creating a semaphore here with the max handlers, and this is the first approach that I explained. We're reading requests from, we're reading the requests that we sort of assume that we have from the slice. For every request, we add one to the wait group. If you're not familiar with wait group, just leave it be for now. If you are and you're wondering why I didn't just add the length of recs to the wait group, it's a great question. The reason is to keep it more closer to the actual pattern that is usually used when reading or receiving requests, right? And we are receiving requests if it's a server from the World Wide Web. We have no idea how many are coming. So we actually usually just add one each time. So I wanted to keep it closer to that. We spawn a Go routine to handle the request, so to handle concurrently, but of course, assuming that we have a finite resource here. And then, so we acquired a semaphore, we handled the request, and we release the semaphore. And then we'll let the wait group know that we're done, so that this wait here at some point is going to release. And then I want to benchmark this. Now, something about, so I have this function handle here. Handle well, it does two things actually. It does, first thing that it does, it actually counts the requests that we're receiving so that I would know that I don't have a bug. And another thing that it does, it sleeps for a microsecond. And this is kind of important. So I'm going to ask a question later to see that you understood what's happening here. And then I created a bunch of benchmarks. Now, so all of these benchmarks are calling benchmark serve a private method here with a number that I think I'm not using actually. No, I am. So we have two changing numbers here. One is the number of messages, and two is the number of Go routines that we want to be able to run concurrently. So the weight of the semaphore. So so to have the number of Go routines change, or to have multiple types of to be able to have the running number on the benchmark test is not the number of Go routines. What I'm getting at, we have multiple tests, one for 10, one for 100, one for 1,000, 10,000, 100,000 for the number of Go routines that we want to run concurrently. And then we use BN, which is the changing number that we receive from the benchmark, from that usually increases until the benchmark is taken too long. We use BN to define how many messages we want to be able to handle. I'm just going to show you what that looks like, and what I'm explaining right now also appears on the README. So this is Sema 1. This is the first example. We're going to use bench time here with X. X means that it's a number of times that we want to run. So basically it will determine this N that we receive in the benchmark. If you use something like seconds here, it will be seconds. So, but when you use X, it's for a number of times, or for the loop count. So let's just run that. Now, hopefully, nothing too bad is going to happen here because I'm running Zoom. Well, okay, it's a bit slower than usual, but you know what? It's fine for a demonstration. So we see that for a low amount of Go routines, it's actually slower, which is what we expected. So we have only 10, when we have only 10 Go routines running concurrently, and we're processing 1 million requests, this is what we get. Now, I want you to tell me something, and now I'm feeling kind of sad that I wrote it actually on the README. But I mean, it says here that it's 1,500 nanosecond per operation. So who can be wise and tell me what we're actually measuring here? Chat people, chat, come on, you can do this. Not even Ole? So what are we measuring here? We have 1 million, yeah, but it's not an operation. What is it then? It's not an operation, because the benchmark we received here, 1 million. So we created here, like, I'm just going to write this down. We created here a number of requests of 1 million. Let me make it easier. So we know that we are sleeping here a microsecond, and a microsecond is 1,000 nanoseconds. So you can see here that it doesn't make any sense. Then one loop could actually take less than that, right? And this one is taking 775 nanoseconds per operation. So how is this? How can this be? What's happening here? What are we measuring here? per operation batch, time it takes per coroutine. So the operation in this particular case is actually how long it takes to handle one message. And because we're handling multiple messages concurrently, we get a number that is lower than the wait time. Make sense, everybody? Good. The average time per n. Well, okay. I'm glad, I'm hoping I made myself clear. So moving on to the second approach. The second approach says basically the same thing. It's exactly the same. So if I look at this one, if I manage to zoom in just right, you will see that there is no difference between this code and this code, but of course I can't. The only difference is that this line, the acquiring of the semaphore, is happening. Here it happened after we spawned the Go routine, so inside the Go routine, and here it happened after. And this is where things get interesting, because I was absolutely certain that this will be slower, except, oh, second, I don't have that. Oh. Nope. Let's look at Sema 2 then.
Your terminal looks a bit
So we can actually see that it's not slower, and for lower ends, it's actually faster, which was very, very surprising to me.
Rana, we can't see your terminal. It's all black for us. Can you maybe make it, minimize it, and then make it big again?
Minimize it?
Yeah, your terminal is black for us. It's nobody can see anything.
Okay, one sec.
Just minimize the window. Or when you select something, then we can see it, but only the selected part.
Oh, that's what you're saying. Well, let's do that then. This is good? No?
Not yet.
Maybe? Okay, I'm just going to copy this so that you will see what I see. If any of you has decided already to clone this, you can actually say, you know what, I have an example. We have the example, not, I don't want Chrome. I'm running way too many things for this thing. Okay, nothing is responding.
It doesn't work. I can stop you from sharing the screen, and you can share again. Yeah, can you restart?
I thought I started a new share. It said I'll try